Hello and welcome back to Build a CubeSat. My name is Manuel and today we are going to talk about how the first test flight of my CubeSat prototype went. And once again, I would like to thank PCBWay for sponsoring this video. As you may know, I sent SN1 up into the stratosphere on a high altitude balloon in early July. The primary goal of this flight was to test the hardware. Unfortunately, this was mostly unsuccessful, and that's a bummer. But it's also kind of okay because that's why we do test flights after all. The most important thing now is that we learn as much as we can from this flight for the next one. And so here is what I would like to do in this video. First, let's talk about how the launch went, what exactly failed, and why I think it did. Then we will look at some of the data I was able to collect, and lastly, we will try and formulate a few preliminary goals for the next flight. So there are two categories of mistakes that I made with this flight, technical ones and operational ones. Let's talk about the technical ones first and do a recap of the launch. On launch day, things started out less than optimal. Just after we arrived at the launch site, the prototype took a tumble when the table it was on collapsed. Luckily, it was integrated into the detachable upper part of the launch tower, which in turn was stored in a padded container. That part is detachable so that the prototype can be integrated well before launch day and transported separately. So the whole thing got shaken around a bit as the table went down, and about an hour before launch, when I pulled the deploy pin on the EPS, nothing happened. I suspected that the old pad misalignment bug that we talked about in the last video caused a short and prevented the battery disconnect switches from turning on. And indeed, as I wiggled the two MCU carriers on the C+ side around a bit, everything lit up. This is probably a good moment to mention that these temporary board holders that I printed are too loose. In hindsight, that's a thing that I should have taken the time to reprint. So the boards were powered, but the first sign of something else not working right was when I didn't get any telemetry over LoRa or LTE after a few minutes. I didn't have a way to connect to the boards while they were integrated, so the only thing I could do was verify that the appropriate LEDs were blinking and hope for the best. The CM5, on the other hand, was uploading stills and telemetry to Firebase, so that at least seemed to be nominal. At T-10 minutes, the CM5 was supposed to initiate a video stream over UDP from Cam1, that's the X Plus facing one, that we could ingest on the Mac Mini at the launch site and show it on the live stream. We did not receive the stream in OBS, however, and I didn't want to risk connecting to the CM5 and potentially break something else. A glance at the temperature telemetry confirmed that something was happening on the CM5 because it jumped by about 5 degrees right around the time the stream was supposed to start. And indeed, after recovery, I found the local recording of that video stream. Going back to the log file, we can confirm that it did start to stream in addition to recording by this line. So why didn't we receive the stream then? I suspect what happened here is that the CM5 was mistakenly connected to the Starlink access point's Wi-Fi instead of the directional antenna. I think that's something that should be fixable for next time. This is also a good moment to mention another error. As we see here, this piece of aluminum extrusion is in focus, which it should not be. I meant to set the focus to infinity and disable autofocus for the flight, but apparently this didn't work. That's something to fix in the flight script and do more ground testing on. And now we get to the first major problem. At T+9 seconds, the recorded stream just cuts off. This could mean a number of things. Either we already lost Wi-Fi and the script switched to LOS mode, so loss of signal, or the script crashed somehow, or we had a power outage or brownout. Let's look at the journalctl log, which stores every print output of the flight script because it's running as a systemd service. If you're unfamiliar with that, systemd is a built-in Linux program that initializes the system and controls background processes. In the past, I have used cron jobs for that, but apparently systemd is the recommended way now. As we see here, each new instantiation of the flight script creates a new numbered log file. I called that sequential number boot, which is not completely accurate because it will also increment if the script crashes and gets auto-restarted by systemd. But in any case, this is log file number 1 since I wiped the testing data before the launch. As we approach 12 o'clock, we see the countdown happening and then the script switches to the flight phase as it should. It runs for another 15 seconds until we definitely lose Wi-Fi and enter loss of signal mode at this line here. So I'm not completely sure why the stream already cut off 6 seconds prior to this, but at least we can verify that the CM5 was still powered and the script was still running at T+15 seconds. Now this is where it gets a bit more interesting. For some reason, when we try to switch flight phase, we get a runtime error that crashes the script. Apparently because of a problem with temporal denoising, which is what TDN stands for. I had not even remotely thought about that setting prior to the flight, so it was just left on automatic and somehow it crashed the script. That's odd but not catastrophic, because systemd restarts the script 5 seconds later. Then we go through the whole initialization again, and as you see here, we reconnect to Wi-Fi at this point, although the signal strength is not great. RSSI is -80 dBm, which is barely usable. So this is at 37 seconds into the flight, and we are at a range of about 265 meters from the launch site. And this corroborates the suspicion that the Raspberry Pi is not connected to the directional antenna at this time, because that should have provided more range than this. And indeed, at the next still capture and upload attempt, we definitely enter LOS mode now. After this, we continue coasting nominally up until sometime between t plus 10 minutes 35 and 13:20, when something causes the CM5 to reboot. At 10:29, the CPU temperature is still at a balmy 7.25 degrees, but the environment will be somewhere between 0 and -10 degrees Celsius, that is. After this attempt to initialize, we don't get too far, and this is the end of the CM5 flight data. Now this is where battery and bus voltage measurements would come in really handy, because this very much looks like either a brownout or an intermittent contact. Both are plausible and both are fixable. My first instinct was that this was a brownout followed by a blackout due to the ambient temperature dropping, and I wondered if the battery voltage dropped too low for the buck converter to regulate. Or maybe the battery voltage was fine and there's just a problem with the buck regulator itself. Or maybe that's fine too and some other component tapped out due to the temperature. I later found out that only the CM5 on the C- side was affected by this, while the MCU carriers on the C+ side kept running fine. This means no system-wide power loss, but rather an intermittent contact on the C- side. During integration, I discovered that I made this C- interconnect just a bit too short. It's kind of hard to see, but right now it's pushed all the way up in the C+ direction, and this gap here is a bit bigger than it should be. I tried to compensate by adjusting these slots up on the 3D printed board holder, but apparently it wasn't quite enough, because this still has some play. So probably the balloon got whipped around as it went up through the layers of atmosphere, and this just got jostled loose, then reconnected and disconnected again. The interconnect length is an easy fix, as I will have to order new interconnect boards anyways because of the pad misalignment bug we talked about in the previous video. So the CM5 didn't come back on for the rest of the flight, but how did the two MCU carriers do? Well, a bit better. Let's talk about MCU1 first. That's the one that has LoRa and GNSS function boards. This is the raw log from the MicroPython script running on the RP2040 processor board. Two things are immediately clear. We are getting GNSS data, but the log's timestamp is off. It's using the RTC as time source, which has lost its configuration and defaults back to January 1st, 2000. What should happen is that it uses the GNSS timestamp, but that's just a software problem. What we can glean from this is that GNSS data gets recorded every 15 seconds, but it's not transmitted via LoRa because that would be written to the log too. So the LoRa failure is probably due to the LoRa function board not being initialized, which means that it may have gotten knocked loose when the table collapsed before the flight. Fixing this is probably quite easy. I messed up the solder nut position by about 1.5 millimeters when I laid the board out, so if the solder nuts were in the right spot, the board would have probably stayed put. To check for this kind of failure, which likely took down LoRa and the CM5 on this flight, I have ordered a concrete shaker. Of course, that's a very different and much less sophisticated tool than a vibration table. A vibration table exposes a test article to very specific frequencies and amplitudes of vibration, often in multiple axes, so that the article's response can be measured and its resonant frequencies determined. What I want to do is to simply shake the thing around and see if anything stops working. This should hopefully help mitigate that kind of problem on future flights. In terms of what MCU1 actually recorded, we'll get to that in a bit, but let's talk about MCU2 first. This one had the Node card LT and GNSS function board and another RP2040 processor board. And it was a bit of a dud. Looking at the log, we see the same problem as before with the time source, but also not much else. The GNSS did not get a log, and so we only recorded the board's temperature and didn't upload anything to NodeHub. My suspicion is that the GNSS antenna wasn't plugged in correctly. I noticed that it was unplugged after the flight, and I doubt that this happened during the flight, so this was probably an oversight during integration. For the lack of telemetry, I would say that it was unable to establish a cellular connection due to radio interference. That's just a guess for the moment, but maybe the DJI for air unit signal overwhelmed the LTE signal on account of the antennas being so close together. In fact, I had never tested running both of them at the same time prior to the flight, so that's something to verify for the next flight. So when I started to collate data after the flight, I was a bit bummed because all of my boards only worked partially, to put it mildly. But then I realized that there was actually another board on the flight that collected and transmitted telemetry, which was this QRP Labs LightAPRS 2.0. This is not something I designed, but a product I bought and included to warn off other aircraft that use APRS, like paragliders. This board sent out location and a bunch of other data at 144.8 MHz, which then got picked up by my Raspberry Pi at the launch site that had an RTL SDR connected and was running the software required to capture the APRS packages and forward them to aprs.fi. I will include a link in the description on how to set this up. Actually, I only had this receiver at the launch site to verify that the APRS transmitter was working, but it ended up providing the bulk of the flight data. So this is the raw log I exported from aprs.fi, and as we see here, the LightAPRS recorded not only location and altitude, but also temperature, ambient pressure, and its battery voltage. The battery voltage isn't too relevant for us, other than we can see that it started out at 4.19 volts and ended up at 3.98, so the size of the battery is more than adequate for this flight profile. Oh, and by the way, the highest recorded altitude is around 31.7 kilometers, so a bit higher than the 30 kilometers expected by the flight trajectory prediction. I intentionally overfilled the balloon a bit to land short of the prediction, so that checks out. Before we get into visualizing the data that the LightAPRS and the other boards collected, I'd like to wrap up telling you about how the launch day went. As the CM5 video stream never came on, we only had the one from the DJI 04 backup camera. That one soldiered on until about T plus 7 minutes 45, at which point it was at range of about 5 kilometers, so not bad at all. In terms of stills, the most exciting thing we got back is this blurry still taken at around 4 kilometers altitude. Definitely some room for improvement there. After the backup video went out and no other telemetry came in, we concluded the live stream, packed everything up, and Anya and I headed out for the recovery. So we had 3 working location trackers, the LightAPRS and 2 spots. All of the data lined up pretty well with the trajectory prediction, so we headed northeast, and sure enough we found the payload in the middle of a field near Landsberg. So it appears we have landed a bit short of Landsberg as we had hoped, and we just drove about an hour, and the landing zone is just off the highway. And right now we are about where, oh yeah, we're over here. Right, yeah, at this corner of the forest, and now we're going to find a way over here through this construction site and onto this field. Should only be about 5 or 10 more minutes, and yeah, I'm hopeful that we're able to recover soon. Apparently it hasn't rained here yet, so maybe the thing is even working still, so we'll see. Almost all PV cells had fallen off and the backup video boom was snapped off, both of which I expected to happen. But other than that, SN1 survived the trip without damage. At which speed it landed is a bit more difficult to determine without the IMUs working. The data we'll see in a bit indicates somewhere around 5 to 7 meters per second both horizontally and vertically, but that's just an estimate. When I picked the prototype up, it was powered down. I just assumed that the batteries had run out, but in fact when I later measured them, they were still at 7.2 volts out of the 8.4 we started with, so plenty of energy left. I'm not too sure why it had already turned off, because the under voltage protection was deactivated and the buck converter should be able to regulate down to 6.5 volts. My suspicion is that the impact caused another short on the misaligned interconnect pads, which in turn triggered the short circuit protection on the battery disconnect switches. Unfortunately, I didn't inspect the prototype carefully enough after recovery to confirm or rule that out. Since then I have removed the side panels and disassembled the C+ side to access the data on the RP2040s. Oh, and this is what the remains of a burst high altitude balloon look like. The latex kind of stringifies and wraps itself around whatever is nearby. This is why you want to have a few meters distance to your parachute. Let's now go ahead and take a look at some of the flight data. By the way, I have uploaded all of this to Codeberg, so if you want to take a look for yourself, the link is in the description. Here we are in Google Earth, and I imported a KML file with the flight trajectory as recorded by the LightAPRS. So each vertical line here is a data point, and as we can see here, there is quite a gap during descent. This is probably just because no ground station was within range there and the data didn't get sent to aprs.py. So for the next flight I may pre-position a second ground station close to the expected landing zone. Now I have also imported the GNSS data from MCU1, and if you look really closely you may notice something. Two things actually. So first off, we seem to have left Switzerland and we're in Austria now. For some reason the latitude is offset by 4.66 degrees while the longitude is spot on, which I don't know. If you have extensive experience with GNSS, let me know in the comments if you have come across an error like this before. Now the other thing is that the altitude seems to be cut off right here, which also had me stumped at first because it doesn't look like the board had stopped recording data. After all, there is another point at the same height right here. To investigate this, I cleaned the flight data up a bit in Google Sheets, meaning I unified all the formatting and interpolated the missing timestamps from GNSS time, and then I brought it into a Marimo notebook. In case you're not familiar with Marimo, it's a bit like Jupyter but with a lot of very nice quality of life improvements. Along with UV, this is probably my favorite piece of new Python tooling that I learned about this year. I have linked their YouTube channel in the description if you want to learn more. So I'm very much a beginner when it comes to analyzing data with Python, therefore I only did a few basic things. The imports in the first cell are what you would expect. Marimo to interact with the GUI, pandas for the data, and plotly for the graphs. Then in the next cell I imported the sanitized CSV files as panda data frames, and after that a really nice feature is that if you just return a data frame or a dictionary of multiple data frames in this case, you get this kind of quick look thing that gives you an idea of the overall shape of the data frame. And if you want to explore even further before actually writing any code, you can use the Marimo Data Explorer widget, which lets you basically preview scatter plots. For example, with this APRS data frame, let's put time on the x-axis and altitude on the y. And apart from this big plot over here to the right that shows the ascent as we would expect, the widget also previews other series of data down here. For example, here we have the ambient pressure decreasing as we rise up in the atmosphere, or over here, the horizontal speed slowing down mid-ascent. Anyways, let's get back to that weird GNSS altitude cutoff. So here we have the APRS altitude in blue and MCU1 in orange. And if we zoom in a bit, we see clearly that the MCU1 altitude cuts off around 12 kilometers, which I found oddly specific. So after a little investigating, I found out that the uBlox M8N, which I used on the board, indeed has a platform setting with various dynamic platform models. Scrolling down a bit in this PDF, we see that the portable platform, which is probably the default, maxes out at 12 kilometers. So what I should have done is set this to airborne, which is a little less precise but goes up to 50 kilometers. So that's another learning for next time, and maybe I won't even have to use that somewhat annoying uCenter software to change that setting, because Jeff Geerling made me aware that there's actually a CLI tool to interact with GNSS modules, and I'll definitely check that out. With this mystery solved, let's go back to Marimo and see what else we see. So next up I plotted the vertical speed in red and the horizontal in blue for both the APRS and MCU1. And this is all over the place. Let's maybe just look at the vertical speed. So zooming in here, we see that the ascent rate at launch was between 5 and 6 meters per second roughly, which is a bit less than the 7 meters per second that it should have been. We did have a bit of wind at the launch site, so maybe this contributed to the slower ascent. Also, this measurement isn't that precise. We'd need to get the IMUs working for a more reliable reading on this. And regarding the touchdown velocity, if we zoom in right here at the end, you see that it's kind of all over the place here too, so I wouldn't say this is very reliable. But we do see that after a few outages during descent, MCU1 came back on at around 3.2 kilometers altitude, and then kept on recording data right up until 11:45, so just before the landing. Finally, we have temperature measurements from the APRS, the CM5 and the node card on MCU2. One neat thing here is that we see a very noticeable temperature increase for the CM5 10 minutes prior to launch, so right when it started the video stream. That's also why I had a cooling fan pointed at it on the ground. Another noticeable thing is this kind of stepping in the node card temperature measurements. I'm not sure why that is. In any case, the temperature decreases as we go up, right down to around minus 44 degrees Celsius for the node card. The CM5 tapped out much earlier and the LightAPRS even went down to minus 45.5 degrees. Now let's also overlay ambient pressure as recorded by the LightAPRS. And here we see nicely that once the atmosphere is thin enough, the devices start to warm up again. That's because without convective cooling, the only way to shed heat in a vacuum is radiative cooling, which is much less efficient. You probably knew this, but that's why overheating is a bigger problem for space electronics than freezing. At least for most components. Lithium-ion batteries, for example, really don't like to be charged in freezing temperatures, so these need to be kept not too cold and not too warm. In addition to the problems we talked about so far, there are also a few I was aware of going into the test flight, like the solar charging not working and the RTCs misbehaving. I talked about those in the integration videos if you're interested. So what do we learn from all of this regarding the hardware? Not much, to be honest. A few months before the flight, I set up some primary goals, or rather questions that I wanted to answer, and unfortunately I wasn't able to check off any of them, and this bothered me quite a bit right after the flight. In a matter of maybe a day, I went through 3 distinct phases. The first one was, oh my god, I will never recover from this and the project is doomed. The second one was basically ignoring all the failures and betting on the future revisions of the board solving all the problems magically. And the third one was the most sane one. It's not optimal, but as long as I learn as much as I can from the flight, it's okay. That's what I settled on, and I still think it's a sane approach. After all, this is a long and complicated project, so stuff is bound to fail. But as long as we keep moving forward, we're doing okay. As I mentioned in the beginning, there were not only technical problems, but also operational ones. So let's talk about these next. A lot of what went wrong boils down to me trying to do too much in too little time and thus overextending myself. For a couple of months before the flight, I worked 12 to 16 hours a day, often 6 days a week, which is simply too much. This led to me being thoroughly exhausted on launch day and frankly struggling to form coherent thoughts, which in turn led to some very avoidable mistakes. Case in point, I forgot to turn on the internal recording on the backup video system, which means that we only have the very choppy footage that got downlinked via radio. This sucks pretty bad because nice footage is kind of important for a YouTube channel. Oh, and next time I will put the DJI 4 antennas on the C- side, which should make for less choppy video. Another mistake that really stung was the telemetry overlay for the live stream. A few days before the flight, I wrote 2 Python scripts. One that would simply display a countdown in the lower left corner in OBS, and another one that would pull data from Firebase and display telemetry in the lower right corner. And both of these worked really well, but the thing was that I simply didn't remember to run them. So no countdown or telemetry in the live stream. So these are just 2 examples, but I'm sure a lot could have gone better on launch day if I had been in better shape cognitively. For example, I even wrote a checklist of things that I absolutely needed to do on launch day, but I just forgot that the checklist existed because I was completely on autopilot. What I really need to do next time is only announce a date for the next test flight when I'm actually ready to fly, and also have someone with me who is familiar with the launch proceedings and double checks everything. I have already asked my friend Marco about that, who spontaneously jumped in when an additional pair of hands was needed for helium loading, and he said he's on board next time. So huge thanks to Marco, because this should make things go much smoother. Oh, and one more thing is that I should absolutely keep a lab journal during testing and integration next time. I mean, it's not a super complex system yet, but still at some point it got difficult to remember what I had already done and what still needed doing. That's everything I wanted to mention in regards to the trials and tribulations with this test flight. There are 2 things though that worked really well. Firstly, everything related to the high-altitude balloon flight. So this includes balloon and parachute selection, helium loading, redundant GNSS trackers, safety features, and recovery. All of that was pretty much flawless. The other thing was the memorial aspect of the flight. I think my friends really appreciated the whole thing, even though most of them aren't too interested in space stuff. Also, I would like to take a second and thank Anya, Leandro, Philip, Jules, Manuel, David and Marco for helping me with the launch. Without them, this would not have been possible. Now let's talk about what all of this means for the next test flight. Generally speaking, I would like to get this set up to work properly before moving on to more advanced stuff. I know we all want to see magnetorquers and UHF radios and deployables and, actually cool space hardware, but I think there is a lot of value in getting the basics to work properly first. My approach remains to make a bit slower but hopefully more robust progress. So for the next test flight, here's what I would like to do. Top of the list is make the interconnects work reliably, so that means no more shorts and hopefully even the ability to start testing communications between the boards. Then I want to make LoRa work and be able to send and receive 50 byte long messages, and also if possible make the LTE node card work. I will leave power generation for later because the way the solar panels are mounted will need to change a bit, which will have an impact on the rest of the structure. And I think I'll fold that into porting the structure from Fusion 360 to FreeCAD either later this year or in early 2026. Measuring the battery voltage and current would be really helpful and interesting. And also, if possible, I will make the IMUs work. I think the change needed there is pretty small, so I'll try and implement that. What I really want to do is collect stills and video from the stratosphere because that's what I'm missing very much for this video right now. And I'll want to improve launch operations. So this basically means managing my workload leading up to the launch in a way that I don't end up semi-conscious. I'll try to improve the stream quality. So this means not only the video quality, but also the script, the OST, so the telemetry overlays. And I think there should be someone minding the chat. And I'll try and make a kind of telemetry dashboard and share a public link to that. I'll have to look into this, but MoLab, the Marimo cloud thing, could be a contender to host this on. In hardware terms, this means new revisions for the interconnects, for the CM5 carrier and for the MCU carriers. And this is what the upcoming videos will be about. Actually, the next one will be a step-by-step assembly guide for this configuration, but the ones after that will focus on the new hardware revisions. So consider subscribing to stay in the loop. If you want to support this project, you will find all the usual options in the show notes, including Patreon and YouTube memberships. There aren't really any perks because I will never paywall anything, but I sure appreciate any help with keeping this project going. Also, you are very welcome to join the brand new Discord server, the link to which is also in the description. Thanks to PCBWay for sponsoring this video, and thank you very much for watching all the way through. Let me know if you liked this episode, and I'll see you in the next one.